Hello, welcome to the next video. This is where we left off. We'd just been talking about how the metallic bonding model explains all the properties that we had listed before. However, I also may mention that the metallic bonding model doesn't explain everything, so there are some alternatives. Let's have a look at them. Okay, although many of the models can be explained by what we call the metallic bonding model, what this is called the lattice model, some things aren't explained. For example, why are some of the metals metallic and others are not metallic? Why is platinum, for example, 20 times denser than sodium? That isn't explained by the metallic bonding. We explain density by close packedness, but we don't explain the relative density of certain things. Okay, so I'm going to explain a couple of ideas to explain some of the properties. The magnetic ones I'm probably not going to talk about. That relates to the electron orbitals, and that's pretty much outside the course here, and it's actually more physics than chemistry. Why is lead quite malleable, whereas iron is tough? Okay, so we explained how it happens, why things are malleable and things are ductile, but we didn't. The bonding model, metallic bonding model, doesn't explain the differences between lead and iron. So we have what's also called the ball bearing model, and what the ball bearing model was to explain the differing metal strengths. So why is lead not very strong, but iron is? And what we're looking at is the metals are made up of areas or grains or crystals, sometimes they're called, where there's perfect packing and there's very few dislocations, and we'll show you what that means in a second, or flaws in the packing, and they can bend easy because of this close packing. And metals with small grains or small crystals have many dislocations and therefore do not bend easy. So it goes back to our bonding model about being able to slide, being lubricated by the delocalized electrons, but it's also relating to how metals are made up of different crystals with different orientations, and it's the way those crystals interact that depends on if something bends easily or doesn't bend easily. So, this is an example of metallic bonding, of the ball bearing bonding model, where you've got a tray of ball bearings, pretty much all the same size. You shake it up, and you can see here that there's certain areas where there's a regular pattern of ball bearings, and so the ball bearings are representing the cations, and they're essentially spherical, and so they will arrange themselves in a particular way. So here we have small areas of perfect packing. So there's a regular pattern occurring here, and then there's another pattern occurring here, and a different pattern occurring here. So this metal will not bend easily because of all these gaps, and I'll draw on it in a sec. Now in this case it's shaken up a bit more, and you can see a very large area there of regular packing. And so this one is effectively will bend easily because all these cations will slide against each other and be fairly happy doing that. So let's just show you what I mean by the areas. So these are areas that I've highlighted that I think have the same sort of packing. So there's small metal crystals, and each of these boundaries are where there's dislocations and where the lattices don't meet perfectly, and that's resists bending. Whereas in this case it's only a couple of large crystals. Now the size of crystals in metals is dependent on a number of things, but you can actually see metal crystals if you polish up a piece of metal, or if you've got an old corrugated iron tank outside, you can actually see some metal crystals on the where the zinc has been coated onto the steel. So these are pointing to all these dislocations or disorder, areas of disorder, vacant sites and dislocations. So where there's no ball bearing, that's a vacant site. Where there's just a meshing and gaps, their dislocations. So this is a picture actually of minerals, metal crystals, and these are the boundaries, and so obviously the atoms are significantly smaller than the ball bearings, but on the atomic scale that's what's happening along these edges here. Okay. Now, how do these crystals grow in metals? Well, when you've got a molten piece of molten metal, so you've got it in a furnace, it's above its melting point, and then you let it cool, what happens first is this is all liquid. This is a sequence of slide going from here to here to here to here. So first of all you get what's called nucleation. So a couple of microscopic crystals, so the cations in a couple of places start joining together, being attracted to each other because it's cooling, and so you're losing kinetic energy, so the cations aren't moving so fast, they just keep away from each other. They're losing energy and they're starting to bind together, and so you get these little mini crystals happening, and they will grow further, and more cations will find that there's certain places for them to go on these crystals. And as it cools, because the cations are getting less energy, they want to be able to bind to these crystals, and you get larger crystals, and then the crystals start interlocking, and this is still molten metal in these places, and then eventually all these will fill in, and you end up with the final product, which are the individual crystals in the metal, which we showed you a picture of before. So the next video is how we go about modifying metals. Cheerio!